Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 12 on linearization.
Derivatives are useful in so many contexts, moving far beyond computing slopes. In this lesson, we'll cover one of the primal applications to linearization. This stems from our understanding of Taylor series. Linearization is the first step in a Taylor series, using the first derivative to approximate.
Thinking of derivatives in terms of linear variation can be frustrating if you're trying to visualize it. It's maybe not so easily visualized, as is slope. However, in some examples, you can really see the variation. Consider the area, A, of a square of side length x. What happens if we increase x by a small amount? The area becomes x squared plus 2xh plus h squared. We can see those terms by increasing the side length a little bit and decomposing the extra area into a pair of rectangles with area x times h and a small square whose area is h squared. So, ignoring the terms in big O of h squared, we see that the linear variation is 2x times h. For a triangle, we would get something similar. Let's say a right triangle with length x and height x. Then the area, 1/2 x squared, has the following variation. A of x plus h is 1/2 x squared plus x times h plus 1/2 h squared. Visualizing the additional area, we can break it up into a parallelogram whose width is h and whose height is x, giving a linear variation term of x times h. The leftover material is in big O of h squared. Lastly, for a circular disk of radius x, we have that the area is pi times x squared. What does the variation look like in this case? A of x plus h is pi x squared plus 2 pi x h plus pi h squared. That means if we increase the area a little bit, then the first order term has area 2 pi x times h, but then you've got this leftover higher order term. How does that work? That's a little harder to see. It's maybe a bit easier if you approximate the circular disk by a regular polygon with many sides and extend those sides out to a height of h. Then you see that there are a number of small triangles left over whose areas will add up to that of a disk of radius h in the limit as the number of sides is going to infinity. These first-order variations are the basis for doing linear approximation. For example, let's say you want to estimate the length of a banister for a staircase. If you know something about the dimensions, let's say it's 13 units across and 9 units high, then that length would be square root of 9 squared plus 13 squared, or the square root of 250. Let's say you want to come up with an estimate for that. I don't know what that exact number is, and let's say I don't have a calculator. Well, I could consider the function f of x equals square root of x, and I do know what the square root of 256 is. So that's 16 squared. To get from there to 250, I could use a value of h, a perturbation of -6, so that from a Taylor expansion, f of 250 is going to be f of 256 plus, well, the derivative evaluated at 256 times the difference, times h, -6. All other terms in the Taylor expansion are of higher order. Well, let's see, square root of 256, that's 16, minus 6 over 2 times 16. That gives us 15 and 13/16 as an answer. And that's not so bad of an approximation. That's about 15.8. The true answer is the same up to the first 3 digits. So in this case, linear approximation works pretty well. Consider a different example. Let's try to estimate pi raised to the 20th power without using a calculator. Here's a hint. If you look at pi squared, that's pretty close to 10. It's roughly 9.86. I'll let you do the math without a calculator to verify that one fact. Having done that, let's consider the function f of x that raises x to the 10th power. And then, if we Taylor expand that function about x equals 10, then we're not too far off of pi squared to the 10th or pi to the 20th. In this case, h, your error, is pi squared minus 10, which, according to our computation, is about -0.14. All right, so in that case, pi to the 20th, which is pi squared to the 10th, is approximately 10 to the 10th plus the derivative of x to the 10th, that's 10 times x to the 9th, evaluated at x equals 10, times h, -0.14. Now, if we simplify that a little bit, we see that we get 0.86 times 10 to the 10th, or 8.6 times 10 to the 9th. That's our approximation to pi to the 20th. In scientific notation, that would be 8.6 E9. The true answer is approximately 8.77 E9. We're not terribly close, but we at least got the number of digits correct and the first digit correct as well. We're within 2%.